So 3.6 is about polynomials. The first thing we have here is the rational root theorem, and the rational root theorem tells us that if a rational root exists, it is a factor of the constant term divided by a factor of the leading coefficient. So I want to take a minute and practice that and write out all the possible rational roots for this polynomial. So the constant term is 35. The leading coefficient is 33. I'm going to list their factors. 1, 5, 7, 35. 1, 3, 11, 33. So the possible factors are all of the numbers on the top divided by all of the numbers on the bottom. So I'd start by doing 1 over 1, which is just 1, 5 over 1, 7 over 1, and 35 over 1. Then 1 over 3, 5 over 3, 7 over 3, 35 over 3. Then 1 over 11, 5 over 11, 7 over 11, 35 over 11, and last but not least, 1 over 33, 5 over 33, 7 over 33, 35 over 33. Now, if these reduce, then you should reduce them. But if we're wondering which one in this list is not a possible rational zero, I would say the first one, because 7 is not a factor of 33, and the numbers in my denominator should all be factors of my leading coefficient. Okay? All right, so then if we are writing a polynomial in factored form, the first thing we should always do is graph and try to see what information we can get from the graph. Next to the fifth. I like to go through and double check these because I feel like I almost never get them right the first time. 20x to the fifth, 138x to the fourth, 362x to the third, 444x squared, 248. See, 248x. 48. My poor kid. She just asked my husband where I went, and he was like, she's working, and she just is now freaking out. All right, so it looks like we have a 0 at -2 and a 0 at -1. I can confirm that on the table. Yep, 0 at -2, 0 at -1. But I want to zoom in on the behavior here, because if you remember back, I guess before spring break, we talked about the behavior and its effect on a factor. So I'm going to zoom in a little. And let's go -4 to 0. Oops. -4 to 0. -5 to 5. Oops. Yeah, no, that's right. Okay, so we can see at -2, it bounces. And so remember that when we have a root that bounces, that means that root has multiplicity 2. So what I know is that I have w equals -2 with multiplicity 2, and w equals -1. I know that I have 2 other roots in there, but I don't know exactly what they are. Like, it definitely crosses right there in -2 and -1. And it definitely crosses right there in between 0 and -1, but I don't know exactly where. So I'm going to stick with the ones that I'm sure of. And so if I was turning these into factors, w equals -2 with a multiplicity of 2 would be factor at w plus 2 and then squared. W equals -1 would be a factor at w plus 1. Now, to find my other factors, I'm going to take the roots that I have and I'm going to use synthetic division to divide them out and try to make this polynomial smaller into something that I could maybe work with a little more easily. So I'm going to move over here and we're going to do our synthetic division. Start with our root at -2. It's -40. So when I do these, I will very often just do the whole thing in my calculator. Really, calculator, come on. There we go. So I'll say, okay, 138 minus 40. There we go. Is 98 times -2 plus 362 times -2 plus 444 times -2 plus 8 times -2. And then you'll know that you've done it right if you get a 0 at the end, because we know that this goes in evenly. We saw it on the table. So we should definitely have gotten a 0 there. Since that 2 had multiplicity 2, I'm going to it out twice. So 98 minus 40 times 66 times -2 plus 112 times -2. Perfect. Okay, so then my other root that I found from the graph was a -1. Oops. -38, 12, -12, 0. There we go. Okay. So in dividing out those three roots, I have gone from a polynomial of 5th degree, divided 1 out, 4th degree, divided 1 out, 3rd degree, divided 1 out, 2nd degree. So what I have here is 20w squared plus 38w plus 12. So in order to get linear factors, I'm going to factor this. So 20w squared plus 38w plus 12. This has a GCF of 2. So then 10 times 6 is 60. Two numbers that multiply to 60 and add to 19 are 15 and a 4. So then these have a 5w in common. These have a 2 in common. And so then these have the 2w plus 3 in common. And then that would leave me 5w plus 2. So those are my last two linear factors. Don't forget to take that coefficient that I GCF'd out before and put it in front. And so if we compare this to the graph, if I set 5w plus 2 equals to 0 and I solved it, I would get negative, right? Negative, you'd move the 2 over, divide by 5. You get negative 2/5, which is probably that root right there. And if I set 2/3 equal to 0 and solve, you'd get negative 3/2, which is that root in between -1 and -2. So I'm going to do the next one pretty much the same way. Before I start, I want to note that if they tell you that you have an imaginary roots always travel in pairs. So if you have one imaginary root, then you also have a root at its complex conjugate. So the roots that we know so far are 5i and negative 5i. Because if you have one imaginary root, you have two imaginary roots, and they are always conjugates. So x to the 6th minus 7x to the 5th, 40x to the 4th, to the 3rd, 7 squared. I already know I messed up that sign right there. X to the 6th minus 7x to the 5th plus 40x to the 4th, 186x to the 3rd, 377x squared plus 50. Okay. So it looks like, based on this graph, that I have roots at 1 and 2, but let's confirm that in the table. Yep, 0 at 1, 0 at 2. I'm going to do this one on a separate sheet of paper because I don't think that I have enough room on this one.
I have a question. Where are you getting the numbers for the table?
What do you mean? That's the table. That's the auto table. If your table's not coming up, go to second and then window and table set your independent to auto. Sorry, I muted you because I was like echoing. So go to second and then window to get to table set and change your independent to auto. That'll give you your table back if it's not there.
Okay.
Okay. So we're going to do synthetic division with all 4 of these roots. I like to start with the easy one. So that'd be 1. Still going to grab the calculator here. Negative 186 plus 34. Negative 152 plus 377 minus 275. Okay. Go again with 2. 34 minus 8 times 2 plus negative 100. Negative 152, excuse me, times 2 plus 225 times 2, 0. Okay. So when we do the imaginary roots, the process is the exact same. Okay. So we're going to bring this down and then multiply 1 times 5i. And then add, but negative 4 plus 5i, I can't combine them, so it's just negative 4 plus 5i. And then multiply. 5i times -4 plus 5i. -25 minus 20i. And then plus 26, -1, or 1 minus 20i. And then times 5i, 100 plus 5i. And then minus 100. It's going to give me just 5i. And then times 5i. -25. Okay. Now, the reason why the i's always come in pairs is because what one will do, the other will undo. 1 times a -5i is a -5i. -4 plus 5i minus 5i is just -4. -4 times a -5i is a positive 20i. 1 minus 20i plus 20i is just 1. 1 times a -5i is a -5i. 5i minus 5i is 0. So we started here with a t to the 6th. Divide 1 out. T to the 5th, t to the 4th, t to the 3rd, t squared. So what I'm left with here is t squared minus 4t plus 1. But they wanted linear factors, and this is quadratic, and it doesn't factor. So in order to figure out what the associated linear factors would be, I have to solve this using the quadratic formula. So t equals a -4 would be +4. 4 squared is 16, minus 4 times 1 times 1 is 4. So 16 minus 4 is 12. 2 times 1 is 2. And then 12 reduces. 12 is rad 4 times rad 3. So that would be 2 rad 3 over 2. We're going to divide everything by 2. So we'd be left with 2 plus or minus rad 3. So now I want to talk about these for a second. To turn these into factors, we move everything to one side to get it equal to 0. So I would subtract the 2 and subtract the rad 3. And that is my linear factor. For this one, I would subtract the 2 and add the rad 3. So I would have t minus 2 plus rad 3. So all of my linear factors, well, we start with this 1. So that would be t minus 1. T minus 2. T minus 5i. T plus 5i. T minus 2 minus rad 3. T minus 2 plus rad 3. Okay. We have a polynomial of degree 5 that passes through the origin. That means t equals 0. And has roots at I, which means that also at -I. 8 minus I means also at 8 plus I. And they gave us 1 point. So first, let's make factors. If you have a root at t equals 0, then your factor is just t. So then this would be t minus I. This would be t plus I. This would be t, and then you'd move the 8 over, so it would be minus 8, and you'd move the negative I over, so it would be plus I. And this would be t minus 8 minus I. Right, because if I said each one of these 5 factors equal to 0, I would get each one of those 5 roots. So the only thing I'm missing here is a leading coefficient. And that's why they gave me this point. Because if I plug in 5 for t, I should get 2600 for g. So 2600 equals a times 5 minus I times 5 plus I times 5 minus 8 plus I times 5 minus 8 minus I. That looks like a lot of really fun multiplication to do, right? Why would we do that like manually though? You paid a lot of money for this calculator. Make it work for you. Okay, so when I plug in all of that, I get 1300. So then that means I have 2600 equals 1300A. So if I divide both sides by 1300, my leading coefficient is 2. All right. So one more, let's review some of our properties of polynomials from before break. So the degree of this is 6, and the leading coefficient is -1. With an even degree and a negative leading coefficient, its end behavior is down and down. So as r goes to the right, k of r goes down, and as r goes to the left, k of r goes down. I am, again, going to graph this. So let's see if we can get any roots from the graph. So negative x to the 6th, 13x to the 5th, 75x to the 4th, 21x, 3rd, 2x, 2nd, 18x. X to the 6th minus 13x to the 5th minus 75x to the 4th minus 321 x to the 3rd squared minus 1808x but minus 1. Okay. Uh-oh. Nope, I used the wrong minus sign in front. There we go. Okay, so I have a 0 out here somewhere in between -5 and -6, but I don't know what it is. I have a 0 right here. It looks at -3. I have a 0 right here. It looks at -2. Double check that in the graph. Yep, -3, -2. Cool. So And then it looks like I have another 0 in between -3 and -2. But the only ones that I know for sure are the ones at -3 and -2. And then I also know 4i, which means I also know -4i. So I know 4i, -4i, -3, -2, -1, -13, 32. Okay. Let's divide these out. Now, this process will get me the zeros, the intercepts, and the factors. So fortunately, even though it's a lot of work, it's a lot of bang for our buck. This is 2, -11, -11 times -2, 75 times -2. Oop, that's a positive 106. Minus 132. It's -2. Minus 2. It's -2. 208. -2, -11. Oh, that should have been a -22. All the way back there. Should always end up with a 0 at the end of these. So if you don't get a 0, then you did something wrong. -75 minus 22. No, that should have been a positive 22. -11, -2. -53. I don't know what I did. Let me do -3. 3, -10. 30, -45. -45, so it's positive 135. Yeah. Like I've done this twice today. I don't know what my issue is. 30. Oh, I wrote this
I'm
down.
getting the same numbers as you.
320. I copied it down wrong. That's what the issue is. Yeah, it's not 123, it's 321. Wow, that'll do it every time. -321 plus 135. I bet it works now that I have the right numbers. Times -3 minus 1022 times -3 minus 1808 times -3. Good to go. Yeah. See it? Look.
Yeah, that makes sense.
321. I wrote it down as 123. That'll do it every time. -1. And then that becomes 2. -8, 16. -29. 58. -128. 256. 208. 16, 0. So there we go. That was much better. Okay. So let's do 4i. -1 times a 4i is a -4i. So then that's just negative 8 minus 4i. I can't combine them. So then 4i times negative 8 minus 4i. 16 minus 32i. And then minus 29. And then times 4i. And then minus 128. And then times 4i. And then a minus 4i. So a negative 4i times a negative 1 would be a positive 4i. Negative 8 minus 4i plus 4i is negative 8. Negative 8 times a negative 4i is a positive 32i. Negative 13 minus 32i plus 32i is negative 13. Times a negative 4i is a positive 52i. Okay, this was to the 6th. Divide 1 out to the 5th, 4th, 3rd, 2nd again. So what I have now is negative 1r squared minus 8r minus 13. Now I'm going to GCF out the negative 1. And I'm going to do the quadratic formula on r squared plus 8r plus 13. So then r would equal a negative 8 plus or minus the square root of 8 squared minus 4 times 1 times 13. Negative 13. No, positive 13. Over 2 times 1. So this is again 4 and 3. 2 rad 3. And then we can divide. So r equals negative 4 plus or minus rad 3. Okay, so my zeros then are, write it down. Negative 3, negative 2, 4i, negative 4i, negative 4 plus rad 3, negative 4 minus rad 3. My factors would be x, r. First of all, I had the negative 1 that I GCF'd out, so that's got to go in front. And then r plus 3, r plus 2, r minus 4i, r plus 4i, r plus 4 minus, I hope I actually wrote down the floor, plus 4 minus rad 3, r plus 4 plus rad 3. And then my intercepts would be these values, but only the real ones. So negative 3, 0, negative 2, 0, negative 4 plus rad 3, 0, negative 4 minus rad 3, 0. But for the intercepts, they want decimals. So negative 4 plus rad 3, negative 2.268, negative 4 minus rad 3, 732. And if I look at those intercepts and I go back to the graph, this negative 5.732 is going to be that 0 right next to negative 6. And this negative 2.286 is going to be that 0 in between the negative 3 and negative 2. So I see it now. Okay. And then the last piece to this question is the easiest piece. The y-intercept, remember, is where x equals 0, or in this case, r. So if I change r to 0, this would be 0, 0, 0, 0, 0, 0, and I would be left with just this negative 1248. So when you are in standard form, your constant term is your y-intercept.